Let us see the sub problem based on radioactivity, decay and half-life. So 1 gram of strontium 90 remains 0.0953 after 2 years. Calculate the half-life period of strontium 90 and how many grams of strontium 90 will be left after period of 5 years. So here we can solve it. So we can use the formula lambda is equal to 2.303 divided by 10 log of n naught by n, and one more formula is t half is equal to 0.693 divided by lambda. So this is the equation is given. So based on that we can solve this problem. So we can see here 1 gram strontium is given after 2 years. Okay, so it remains after 2 years. So here we need to, so before half-life we need to find lambda. Okay, so how to find lambda? So here we can solve it. So if we take 2 years, so we will get here about the value of decay constants 2.303 and time is take 2 years. So after 2 years we are getting 1 by 0.953. So 0.953 is given this value. So on solving we will get here 0.24 per year. So the constant is the unit. Then we can use unit, you can use this unit over here, 693 divided by over here. So the decay constant is 0.024. So answer will be 28.88 years. Okay, so question is how many grams of strontium will be left. Okay, so this is the decay. So how many strontium will be left? So we have to find the n value. So n value means after 5 years how many it will be left. So we can write here when t is time is given here 5 years. So in 5 years initial is 1 gram, but and we don't know, so we can put here a value. Decay constant is given 0.024, 2.303 and time is 5 years. Log we know that 1 by n. So on solving n we can get here 0.887 gram. So this is the strontium value after 5 years. So we can take another problem. So prove that the time taken in 99.9% of the radioactive decay is about 10 times to its half-life period. So we have to prove that. So it should be half-life should be 10 times of half-life. That is the time taken by this one. Means they're asking T of 99.9 is equal to 10 times of half-life. So this we have to need to prove that. So we have to take two value. One is T 99.9 and one is T half. So T 99 is 2.303 lambda log. So this is in percentage. So right here 100 and again 100. So 99% is had been decayed. So 99.9. So ultimately we will get here 2.303 lambda and log of 100 divided by 0.1. Similarly you take T half. So 2.303 lambda and you know that this is log 100 minus 50. Okay, so here we will get log 1000. Here we will get here 2.303 by lambda and this will log 10 by 1000. So this is the one equation. This is the second equation. So okay, so dividing equation 1 by equation 2. Okay, we can divide it. So it becomes T 99.19 and divide by T half. So this will be your, only if you divide it, so this will cancel, so this will becomes log, this is your 1000 and this is divided by log 50. Okay, so log 1000 divided, so this will be your log 50, so this will be log 2. Okay, so answer on dividing you will get answer here. This is nothing 3 by 0.3010. Okay, and which is almost equal to 10. So T 99.9 is equal to 10 times of T half. So hence it is proved. Half-life of cesium 37 is 30 years. What amount of cesium will be left behind after 120 years starting from 1 milligram of cesium 37? So half life is given here, and after 120 years, so we can find first number of half lives is, number of half lives will be 120 divided by 30, so this will be 4. So amount of cesium left, after 4 years will be n divided by n naught. So this is equal to 1 by 2 to the power n. So this is the basically formula, and we know that, and this is your nothing but 1 by n whole 4. So this is 1 by 16. If you solve it, so you will get here 0.0625 milligram. So this is basically our answer. So we'll see next problem. So half-life of the radioactive substance is 60 days, and a sample of it contains 1 mole of nuclide. So sample contains 1 nuclide, and calculate the number of disintegration in first second. So in first second, how much number of particle has been decayed? Half life is given, sample amount is also given. So we have to find the disintegration percent, that is dN by dt. So rate of decay, okay, that is R is equal to minus dN by dt, that we know that, okay. So it will be your lambda into n naught, okay. So we have to find lambda also, and n naught is already given here 1 mole, okay. So how much will be there? So lambda equal to, so half life is given here, so lambda we can find out 693 divided by t half, that is nothing, 693 divided by 60. So we will get here day, okay. So now this we can convert day into second, because if we will get converted into second, so we can write here. So day means how much is there, so multiplied by 24 multiplied by 60, 24 day, then convert into hour, convert into second. This will be your total seconds. So we can say here, so in 1 second how much it will be? This is the per second. So for rate will be for rate of decay for first second, so it will be your R equal to, that is for 1 mole of nuclide, that is equal to 0.693, and divided by this value 60 into 24 into 60 multiplied by 60, and the value of 1 mole is 0.23 into 10 to the power 23. So if you solve it, it will be 805 into 10 power 16 disintegration per minute. So this is the first. We have to solve for 1 mole. So keep in mind, we have to take value 1 mole. So an element X which is radioactive and half-life T half is 20 days. Half-life is given. The daughter nuclei formed after decay is X is this much, A minus A minus 12, Y is Z minus 6, means 6 atomic number is reduced by the 6. So calculate the volume of helium collected at STP after 40 days if 2 mole of X is placed in a sealed tube. So mole is also given, 2 mole. So in 2 mole how much it is decayed? So we have to collect helium. So first we see the reaction. So reaction is, if you write it X, so this is the atomic number, so it is decayed into Y, this is A minus 12 and Z minus 6. Z minus 6 is there. 6 means definitely helium is coming out. So this will be 3 mole of helium, 3 into 2, 6. So 1 mole is giving here 3 moles of helium decayed. So we have to find how much moles of helium is converted to gas. So we can find out here, use formula n equal to n naught and 1 by 2 to the power n. So we'll get here number of half-life. So number of half-life is how much we are getting. Number of half-life is nothing but total half-life is given here 40 days. So divide by 40 and divide by 20. So here we get number of half-life 2. So we can apply here n is equal to 2. So we can put this value over here. So 1 by 2 whole square. And n, we know that n is the 2 mole. So n is equal to n naught. So n naught is how much? 2. So this will be 1 by 4 into 2. So we will get here half mole. So half mole is remaining. So amount of helium decayed will be how much? Amount of helium decayed will be 2 minus half mole. So this will be your 1.5 mole. So this is converted into gas. Okay. So now, but how much moles of helium required? How much moles are required? So 1 mole is giving 3 mole. 1 mole is giving 3 mole. Okay. So it will be 1.45 into 3 mole. So this much amount of helium will be present, because 1 mole is giving 3 mole. So we are getting how much? 1.5 moles decayed. So if this is your so for 1.5, how much will be there? So definitely it will be 1.5 into 3 for 1 mass. So volume of helium at STP will be how much? So we know the volume, and we know that at STP it is requiring 22.4 liter. So multiply into 22.4 liter. So we will get here 100.8 liter. So this much amount of helium will be collected at STP in the sealed tube. Now next is, at time t, the activity of the radioactive substance is 4750 disintegration per minute. So this is given here. At time t, the activity is given 4750 and it is reduces to 2700 dpm after t plus 5 minutes. So calculate lambda plus half-life of this substance. So again is easy. So we can solve here. So we can see rate is equal to lambda into n. So we can take two cases. So case 1, one case for 4750, one case for 2700 dpm. So case 1 is r naught is equal to lambda into n naught. So one case r naught we are knowing 4750 here lambda and n naught. Second case 2 we can see here rt, and you will take here lambda into n into t. So second case is 2700 lambda into n into t. Okay, so now we can divide r naught by rt. So it will be 4750 divided by 2700 is the value. Now we see here time is equal to how much? 2.303 divided by lambda and log of n by n naught. So answer will be here. Time we know that. So after t plus 5 minutes, so 5 minutes is given 5. So 2.303 and divide by lambda and log. So n by n naught, this is nothing but the n naught by, so this is your 4750 by 2700. Okay, so this will be your nt by n naught. So this is your n naught by n. So n naught by n, so here you can write here 4750 divided by 2700. So n naught by nt, so this is given here. So we can put directly over here. So on solving, we will get here 0.113 per minute. Now we can calculate the half-life. So half-life will be 0.693 divided by lambda, which is nothing but 0.93 divided by 0.113. So here we get here 6.13 minute. So this is our answer. One answer is this one and second answer is this one. So calculate lambda half-life and average of the radioactive substance whose rate of decay is 3.02 into 10 power 6 dpm at the time of 10 minutes, and after next 10 minutes its rate of decay reduces to 1 by 2 into 10 power 6 dp. This is integration per unit. So here we have to take again two case, case 1 and case 2. So again same thing, r1 is equal to lambda into n1, as second r2 will be equal to lambda into n2. Two cases given. So r1 by r2 will be here, n1 by n2, lambda is constant, so n1 by 2 value is given 10 power 6 divided by 1.2 into 10 to the power 6, so total will be your 3.52. okay, so now we can see, so for T1 means first case rate 1 will be 2.303 divided by lambda and log n naught by n. okay, so take here case 1. So case 1 they have given t is equal to time 10, so time is equal to 2.303 by lambda, that is equal to log n naught by n1. As second case 2 is given, that is 20 is equal to 2.303 lambda and log here n naught by n2. okay, so now we can subtract this one. Subtract, you can subtract here 2 minus 1, subtracting 20 minus 10, so this will be your common 2.303 lambda, and this is your log n naught by n1 minus log n naught by n2. So on solving you can get 2.33 lambda and log n1 minus n2, and we have already calculated n1 by 2 n3 over here. You can see here we already calculated, so we can put the active value 2.303 lambda log, so here will be value 2 point, so this is your 2 point value, actually 2.52, so you will get value lambda equal to 0.92 per minute. So okay, this we are getting, so this is the answer. This one 20 minus 10 is 10, so this is our value. So again you find the half-life, so half-life will be 0.693 divided by lambda, so this is your 0.693, and lambda we know decay constant is 0.092, so we get value here 7.5 minutes per minute. And again average, so this is t average, so t average we are getting 1 by lambda, so again you divide 1 by 0.92, so we will get here 10.87 per minute. So we get here three values together, 1, 2 and 3 values. So activity of the radioactive substance is reduced to 6.25% in 160 days. Calculate lambda and t half. So this is given activity of substance. So activity we can write very easy questions. So n by n naught is equal to 1 by 2 to the power, that we know this value, where n is the number of half-lives. So activity 6.25%. So already this has been reduced. So total we have taken 100, and number of half-life is 1 by 2 divided by n. So if you solve it, so this will come here. So n is equal to almost 4. Okay, and 160 days they have given, so this means that this is equal to 160 days by what time. So total time will be your 160 by 4, so this is your 40 days. Okay, so 40 days is the actually half-life. So this is actually half-life is given. So half-life is 40 days. Now we can find out lambda is equal to 0.693 divided by 40, so you will get here 1.73 into 10 to the power minus 2 per day. So this is our answer. So these questions are very easy, we can solve it. So like this we can solve it. So we'll get this our answers.